Hey everyone, Professor Cameron here. And what we're going to be talking about today is fasteners and threading and how that works with SolidWorks. So, if we look at our final project, we have quite a bit of threading on here, and we haven't gone over how to do any of that. So, when we look at something like this thread callout right here, 0.625-8 Acme, um, it's not quite clear right away what that means to us, but what we're going to do is we're going to go through what each of these numbers means, and then in the next video, we're actually going to go through how to model the threads for this vice screw, and consequently, how to model the threads for the mating thread in the base. But we'll talk a little bit more about modeling techniques and how we're going to model that in the next video. What I'm going to talk about right now is just general threads and fasteners. So threaded fasteners, that's going to range anything from, bolts and nuts, screws, um, stuff like that. And the reason why we use threads is for two reasons. One, we use them as an assembly means, as a non-permanent means of assembly. So we use them for stuff that we want to be able to put together and take apart, stuff that we don't want to weld or glue together. Secondly, we use threads for transmitting power, which is what we're actually using them for in this vice screw. We're transmitting motion energy to create the actual clamping motion. And we have different types of threads for each of those. And we're going to talk about those. So when it comes to threads, there are two types of threads. There are male threads, which we have on an exterior surface like a screw, and we have female threads, which we have on an interior surface like a nut. And we denote these with an A and a B suffix. So if on your thread callout, like you would see right here, we have 1/4 20 UNC-2A. The A indicates that this is a male thread. The B, if you see a B here, that would indicate that it's a female thread or an interior thread. And there are important reasons why we need to know that, specifically when it comes to how we model these. Now, before we talk about that, let's talk about the thread terminology. So, when we look at a thread, there are a few numbers that we have here. This 1/4 20, the 1/4 inch right here, or this first number, whatever it happens to be, this is what we call our major diameter. This is the largest size this thread will be. And on this male thread that I have here, it's the distance from peak to peak. So if you were to take a pair of calipers, measure this at its widest point, that would be the major diameter. And anytime you see a thread call out, the first number is always your major. So we know what size the material is. The next number here, this is what we call our threads per inch, or our TPI. Now our threads per inch is how many threads, how many actual individual peaks are in 1 inch of space. So on this thread here, this is a 1/4 20 thread. In 1 inch of space, there are 20 thread teeth. Now, what that leads us into is our pitch. And our pitch is our distance between thread teeth. So since we know that there are 20 teeth in 1 inch, the distance between each tooth is 1 inch divided by your threads per inch. So in this case, it's 1/20 is our pitch. That's going to be important when it comes to modeling threads, but we'll touch on that in our next video. This third bit here, UNC, What this talks about is what type of thread that we have, because we have different thread forms. We have Unified National Screw Threads, which is what UNC is. So UNC is Unified National, and then it's a coarse pitch thread. Unified National being the shape of the thread. We also have threads for metric, and these are essentially the same. These are general use threads, meaning we use them for pretty much holding parts together. If you go ahead and buy a screw from Home Depot, it's going to be either a unified national thread or it's going to be an ISO or a metric thread. The goal for these is the same. We also have threads for power transmission. So for that, we have a square thread, an Acme thread, which is what we're going to use on our vise. And the difference between square and Acme is essentially the strength of the threads. If you look at the Acme thread compared to the square thread, you can see that the Acme thread is a little beefier. It's a little more substantial. So these are generally a little bit stronger. You'll see both used equally when it comes to bench vices. And then we have buttress threads. So think of these kind of like Acme threads, except they only work in one direction. The Acme thread is designed to handle load in both directions. The buttress thread is designed to only handle it in one direction. So we use this on stuff like truck jacks and automotive lifts and stuff like that, where you're only supporting load in one direction. There are a whole slew of other threads like Whitworth threads and knuckle threads, but the main ones are going to be UNC, Unified National, Isometric, Square, and Acme. Now, the difference between all of these, as far as Unified National threads go, is essentially the shape of the thread in regards to the threads per inch. So you're typically going to see UNC and UNF. And for our purposes, there's really not much difference between the two. Now, so we have our major diameter, our threads per inch, our type of thread that we have, and then we come into this last portion here. We already know the A denotes that it's a male thread. But what is this 2? This 2 is essentially the tolerance or the thread class on our threads. So it'll be either 1, 2, or 3. A class 1 fit is the loosest type of fit. This means that there's a lot of space between the male and female teeth, and you'll typically see this on larger industrial threading. Typically larger than a 1/4 inch. You'll see it a lot on farm equipment. Stuff that needs to be able to fit together when there's a lot of dirt and debris interfering with those threads. Class 2, this is your standard thread class. It's a little bit tighter than class 1, so there's less slop between the teeth. And this is just used for general purpose bolts. If you go ahead and buy a thread from Home Depot or you buy a screw from Home Depot, chances are it's going to be a class 2 thread. And then class 3, this is the closest fit. This is where there's very little slop between the male and female threads. And we use this where precision is required. So a lot of threading in fine equipment, like watches and timekeeping and stuff like that, is a class 3 fit. And it also withstands stress and vibration. I'm sure you guys have all had a situation where you've had a part on a bicycle or a car or something shake itself loose out over time. Class 3, they fit together really tight, and it's a little more resistant to that. So, major diameter, threads per inch, thread type, thread fit, and then whether it's a male or female. Now, like I was talking about earlier, there's going to be a difference when it comes to modeling male and female threads. And we're going to touch on this more when we actually model threads in our next video. But we also have to take into account the minor diameter. So the minor diameter is essentially the polar opposite of the major diameter. We have the root to root distance as opposed to the major diameter, which is the peak to peak distance. Now, because of how we manufacture threads, that's going to dictate which one we use when we're selecting stock or drilling holes. When we manufacture male threads, typically what we do is we'll start with a piece of stock that's our major diameter. So we're going to start with a piece of stock that's a 1/4 inch in diameter. We're then going to come in here and cut these threads out. And we have a few tools to do this. We can do this on a lathe, or we can do this with a threading die, which will cut away this material. But because we're removing material, we need to start with the major diameter. When it comes to female threads, that's a little bit different. So what we're going to start with is a hole that is our minor diameter. And then what we're going to do is we're going to run through here what we call a tap. And that tap is going to cut in those threads into that minor diameter. So when we model in SolidWorks, when we model male threads, we're going to model them at the major. When we model female threads, we're going to model them at the minor diameter. Now you can look this information up on a tap chart. A tap chart will look something kind of like this here. It will list your thread type, so 1/4 20. It will list your major diameter and your drill size or your minor diameter. Now, when you look at a tap chart, one thing you'll notice is that for anything below a 1/4 inch, so all these sizes here, we don't list them as fractions like we do normally. We list them in terms of gauge number. So on our PDF for our vice screw, we have this thread right here. Diameter 21624 UNC. Nowadays, we list that according to gauge number. So when we look at our chart here, 216 diameter equates to a number 12. So when we're doing threading in SolidWorks or when you're buying a screw, you're going to buy a screw called a number 12 -24. Just something to keep in mind. A lot of times people run into issues where they can't find the right threading because they're looking for 216, they're looking for the decimal or the fraction equivalent. We don't do it that way. We list them according to gauge number. So number 12, 10, 8, so on and so forth. So that covers the threading. So let's look at an example of this. We just did a 1/4 20 example. So right here, we've got this thread here. It's 0.5-13 UNC-3B. So 1/2 inch, that is our major diameter. 13, number of threads per inch. So in 1 inch of space, 13 threads. Unified National Coarse. This is a type 3, so it's a very tight fitting thread. And it's a B, so it's a female thread, so it's a threaded hole. Now, when it comes to threads and fasteners specifically, we have to accommodate the screw head. And there are two common types of screw heads. There's what's called a socket head cap screw, or a socket head screw, and there's what's called a flathead screw. So a socket head or a button head cap screw is going to have a flat shoulder here and then a head here. The flathead is going to have a sloped shoulder, and we denote how we countersink these and counterbore these differently. The reason why we have to countersink and counterbore is, let's say we have a situation where we have a flat piece and then just a straight hole. All right, and we'll say that this is threaded, right, like that. If we use a flathead screw, that screw is going to fit in here, but there's no relief made for the actual head of the screw. So you're going to have the head of this screw sticking up. And that poses two issues. One, it's not flat, right? So we can't mount anything on top of this. This is going to catch on things. Secondly, this isn't actually holding well because the screw generates its clamping force from this area here and here. And if that's sticking up above the surface, it's not actually doing its job. So what we have to do is when we cut this thread, we have to cut in a bevel like that. So that way our screw head will fit in here. And it has a surface where it's sitting below the surface, but it's also able to transmit that clamping force equally here. Now, we call that a countersink. So a countersink is the beveled one. And we denote that with a countersink symbol. It looks like a V. So we'll see that on a drawing like this here. So what you will have is you will have your hole diameter and your depth, typically. Underneath that, you will have a countersink symbol. It looks like a V, the diameter, and the angle. Your angle is almost always going to be 82 degrees. I'll talk about why we would change that in a second. But this diameter here, that is the diameter at the widest point. Now, like I said, this angle, which is the angle here, it's almost always 82 degrees. That's pretty much a standard. However, there is a situation where we would want a shallower angle. And that is if we were dealing with thin pieces. So if we have a really thin piece like this, and we have an 82 degree, it's a little steeper, so it's going to come in something like this. All right? The problem is, if that is thin enough, the screw head will actually poke through before it gets to the threaded portion. And we don't want that, right? Because we have this area here that's protruding through and it's not contributing to clamping. So what we're going to do is we're going to put in a shallower angle. So it'll look something like this. This angle is almost always going to be 100 degrees. So we have two options, 82, which is sort of the standard. And then when we're dealing with shallower parts, we'll put in a 100-degree head, and we'll have to buy screws that match that 100-degree angle. Right like that. So I hope that illustrates the difference, but almost always going to be 82 degrees. And then this number right here, this diameter, like I said, this is going to be the diameter at the widest point up here. So that's for flathead screws. We put in what is called a countersink. Now for socket head screws, we put in what's called a counterbore. And we denote that with this sort of wide, flat U symbol. Looks kind of like an upside down staple. The notation for this is more or less the same. What we have is our hole parameters for our hole. So this is a diameter 0.397 through wall, so it's a through hole. And we have the counterbore symbol. We have the diameter for the counterbore symbol. And because this is just a straight cut, we use just the depth. And that's typically going to be the depth of the head plus a little bit extra. Now, SolidWorks has a feature that will calculate all of this for us, and I'm going to show you guys that in the next video. So no need to worry about figuring out what size screw head you guys have to use. But again, that allows that screw to sit flush underneath that surface. You'll also hear something called a spot face, which is similar to a counterbore, but it's not intended to do the same thing. So picture we had a sloped surface like this, and we needed to drill a hole here. Well, when we go ahead and attach a screw to this, that screw head is only going to make contact at one point right here. This right here is not touching our piece. And what that means is we're not getting a full clamping force out of this screw. So what we do here is we put in what's called a spot face. And a spot face is very similar to a counterbore. However, it's not as deep. And all it's designed to do is to give a flat spot here for that screw to sit so that we can get a full clamping force out of it. So they're typically very shallow, and they're going to sit here just like this, so that this gets full clamping on this curved surface. So you'll occasionally see S-face or spot face on drawings as well. So we've covered threading, major diameter, threads per inch, thread type, fit, male, female, and we've covered screw heads. So in our next video, we're going to talk about how we implement this in SolidWorks. But if you guys have any questions on any of this, please let me know. And as always, have a nice day.